Hi everyone, thank you so much for clicking onto the video. Today we're going to be learning about dynamic equilibrium and Le Chatelier's principle. So these are our learning objectives. Firstly, to explain that a dynamic equilibrium exists in a closed system when the rate of the forward reaction is equal to the rate of the reverse reaction and the concentrations of reactants and products do not change. And then Le Chatelier's principle and its application for homogeneous equilibria to deduce qualitatively the effect of a change in temperature, pressure, or concentration on the position of equilibrium. Then we're going to explain that a catalyst increases the rate of both forward and reverse reactions by the same amount, so resulting in an unchanged position of equilibrium. Then we're going to discuss how the techniques and procedures used to investigate changes to the position of equilibrium for changes in concentration and temperature. And then we're going to explain the importance to the chemical industry of a compromise between chemical equilibrium and reaction rate in deciding the operational conditions. A reversible reaction is a reaction that can be made to go in either direction depending on the conditions. So, for example, we could have calcium carbonate being heated to form calcium oxide, the solid, and carbon dioxide gas. Now, in an open system where the carbon dioxide gas is allowed to escape, this would just be a one-way reaction. It would just be from left to right. However, if we used a closed system, so we had it in a box, for example, so if we had some calcium carbonate in a box and heated that, and what would be produced would be the calcium oxide and the carbon dioxide gas. But these products aren't allowed to escape from the system, and so they actually react together to reform the reactant, which is the calcium carbonate. And so we have the forward reaction and we also have a back reaction. And so it becomes a reversible reaction when we use a closed system. And we use this notation for reversible reaction. So this top arrow signifies the forward reaction. And this arrow signifies the back reaction. So the equation would look like this. And the reactant forms the products, and the products react to reform the reactant until an equilibrium mixture is reached. And what an equilibrium mixture is a mixture where the forward reaction occurs at the same rate as the back reaction. And this isn't necessarily when all the concentrations of the reactants and products are the same. It's just when the forward reaction is at the same rate as the back reaction. However, the concentrations of each reactant and each product must remain constant for it to be in equilibrium. So now I'm going to talk about Le Chatelier's principle, and it states that if a dynamic equilibrium is disturbed by changing the conditions, then the position of equilibrium actually moves to counteract that change. So a dynamic equilibrium is a reversible reaction which is in a closed system where the rate of forward reaction is the same as the rate of the back reaction. And this is actually caused because at the start there's lots of reactants. So the rate of reaction of the forward reaction is very quick, and that's because there's lots of reactants. But then once they get used up and more products are made, then the back reaction gets quickened. And they actually balance each other out in the end. So they form an equilibrium where the rates of both forward and back reactions are the same. So we can use this principle to predict the effects of changes in temperature, pressure, and concentration on the position of equilibrium in homogeneous reactions. And the meaning of homogeneous is that all the reactants and products are in the same state as each other. So the first thing we can alter about a reaction is if we use catalysts or not. And actually, catalysts have no effect on the position of equilibrium because all they do is provide an alternative route with a lower activation energy for the reaction to happen. So it actually allows the equilibrium to be reached more quickly. And because of this, it's very important for industry because it saves them money because the equilibrium is reached more quickly, and so they get their products more quickly. So basically, the catalysts speed up the reaction of both forward and back, so it just cancels out, so it has no overall effect on the position of the equilibrium. So the second thing that we can alter about a reaction is the concentration. So the way in which we can change the concentration of different species, so either like the reactants or the products, is by adding more or by taking out. So for example, if we added in more of A, then we would increase the concentration of A. And by Le Chatelier's principle, the equilibrium should shift to counteract this change. So adding more A would mean that equilibrium would shift to the right to produce more products. And if we added more of B, it'd do the same thing. The equilibrium would shift to the right. If we took away some of C, so the concentration of C decreases, again, the equilibrium would shift to the right because it wants to counteract this change. So therefore it creates more products and it creates more of C. So the third way in which we can alter a reaction is by altering the pressure. And this only affects gases. And also, one thing to note is that the equilibrium will only be changed if there are a different number of molecules on each side of the equation. So for this example, the equilibrium can be changed because there are 2 moles of NO2 on one side and 1 mole of N2O4 on the other side. So increasing the pressure is actually equivalent to increasing the concentration. So as we increase the pressure, the equilibrium favors the side with the least number of gas molecules, and so decreasing the pressure will move the equilibrium to the right. Because if we decrease the pressure, because we have less moles of the N2O4, we have 1 of them compared to 2 moles of the NO2, then it will favor the side with the more gas molecules, and that turns out to be the 2 NO2 side. So that means that the equilibrium shifts to the right. The opposite thing happens when we increase the pressure. So when we increase the pressure, it favors the side with the least gas molecules, with less gas molecules. And so that means that the equilibrium shifts to the left. So always remember that when we decrease the pressure, it favors the side with more gas molecules to kind of increase the pressure back to original. And when we increase the pressure, the opposite happens. So it favors the side with the less gas molecules so that the pressure can go down back to what it was before. The fourth way of altering a reaction is by altering the temperature. And this one's a bit more complicated because it depends on whether the reactions are endothermic or exothermic. So as a recap, an exothermic is a reaction with the negative enthalpy change, and it increases the temperature of the surroundings because heat is given off. And endothermic reactions have a positive enthalpy change, and they take energy in, so the surroundings are cooled. So if we increase the temperature, then the equilibrium by Le Chatelier's principle should work to decrease the temperature. So that means that it would favor the endothermic reaction because that would cool. So if we increase the temperature, then what that does is that the equilibrium works to decrease the temperature, so to counteract the change. And the reaction that decreases the temperature would be the endothermic reaction, because endothermic reactions take energy in to form the products. So that means that the equilibrium favours the endothermic reaction, which in this case is the back reaction. But of course that will be different for different reactions. And then the opposite thing for decreasing the temperature. So if we decrease the temperature, then the equilibrium works to increase the temperature, so to counteract the change. That's what Le Chatelier's principle states. And then that means that the equilibrium favours the exothermic reaction, because that increases the temperature of the surroundings. And so for this example, the forward reaction is favoured. And we say that when the equilibrium favours the back reaction, for example, for increasing the temperature, we say that the equilibrium shifts to the left. And for decreasing the temperature, we say that the equilibrium shifts to the right. So a really important thing to know is that for a reversible reaction used in an industrial process, a compromised temperature and pressure is used. We can use the Haber process as an example. So in the Haber process, we combine nitrogen and hydrogen to form ammonia, and this is used to make fertilizers and explosives. So the forward reaction is an exothermic reaction because the delta H is negative here. And that means that the back reaction is endothermic. And so using a very low temperature actually produces a greater yield of ammonia. And that's because when we lower the temperature, the equilibrium shifts to raise the temperature. And so it favours the forward reaction. So the whole equilibrium shifts to the right. And so we form more ammonia. But using a very slow temperature, using a very low temperature can be really slow, and this slows the rate down. And so that's why we use a compromised temperature of 450 degrees. Because that way we can get a high yield of ammonia, but also the reaction won't be too slow to cost lots of money. The second point is that if we use a high pressure, then that produces a greater yield of ammonia. And that's because we have 4 moles of gas on this side and 2 moles of gas on this side. So if we increase the pressure, then the equilibrium favours the side with the least gas molecules because it wants to decrease that pressure. And so the equilibrium shifts to the right again, like for the temperature. And so there's a greater yield of the ammonia. However, a compromise has to be used, and that's due to safety implications and also the cost of producing such high pressure. And so the pressure we use is 200 atmospheres. An atmosphere is just a unit of pressure. So now we're going to move on to some questions. The first one says, this graph shows how changes in the temperature and pressure affect the equilibrium yield of ammonia in the Haber process. So question A asks us, why do we need to find a compromised temperature and pressure? Well, from the graph, we can see that if we use a really low temperature, such as 350 degrees Celsius, the yield of ammonia is the biggest. However, if we use such a low temperature, it would cost the building running the plant a lot of money because the rate of reaction is very, very slow. And so they would have to pay for stuff like lighting and staff members to monitor the reaction. And for pressure, if we look at the graph again, if we use a higher pressure, such as 400 atmospheres, we get a bigger yield of ammonia compared to if we use 100 atmospheres, just looking at this 550 degrees Celsius, because the yield is at about 12% for 100 atmospheres, and for 400 atmospheres, it's about 21%. So it's a lot of difference, but running at such high pressure is actually not very safe and also very expensive. So that's why we need to find a compromise of temperature and pressure so we can get a good amount of ammonia so the yield is quite good, but it won't cost too much. For B, what temperature should we use and why? For the Haber process, it's good to just remember the pressure and the temperature because it comes up quite a lot. So for B, we normally use a temperature of 450 degrees Celsius. And this is because it gives us quite a good yield, but isn't too low a temperature so that the rate of reaction is very slow and it costs us a lot. For C, what kind of pressure should we use and why? So the pressure we use is 200 atmospheres. And that's because it's a good balance of having a good amount of yield of ammonia, but also not being too high for it to be unsafe and for it to cost lots. So if we were using the 450 degrees Celsius and the 200 atmospheres, then our yield would be about 36%. So it's not too bad. Now, the catalyst that we use in the Haber process is actually iron. And what it does is that it just speeds up the rate of reaction. And so it should save the company money. Before we start with number 2, feel free to click off the video and try it out for yourself first. So in which of the following reactions will the position of equilibrium be affected by changing the pressure? So what we need to remember is that with pressure, it can, first of all, it can only apply for gases. And second of all, it only affects the position of equilibrium if there are a different number of moles of gas on each side of the equation. And so we can see that A has 2 moles of gases on the right and 1 mole of gas on the left. So that means that for A, yes, the equilibrium will be affected by a change in the pressure because there are a different number of moles on each side of the equation. And then for B, we can see that we have 2 moles on the left-hand side and also 2 moles on the right-hand side. So that means that no, the position of the equilibrium won't be affected by changing the pressure because there are the same number of moles of gas on both sides of the equation. Hi everyone, thanks so much for clicking onto the video. We're going to look at some harder questions for the topic of equilibrium. So the first question says, the equation for the formation of ammonia is shown below. Experiment A was carried out starting with 1 mole of nitrogen and 3 moles of hydrogen at a constant temperature and a pressure of 20 megapascals. Curve A shows how the number of moles of ammonia present changed with time. Curves B, C, and D refer to similar experiments, starting with 1 mole of nitrogen and 3 moles of hydrogen. In each experiment, different conditions were used. For A, on curve A, mark the point that represents the time at which equilibrium is first reached. So we know that equilibrium means that, first of all, the forward reaction and the back reaction have the same rate. And second of all, that all the concentrations of the reactants and products remain constant. And so the point where A reaches equilibrium must be here, because that's when the moles of ammonia becomes constant. And from that, we also know that the moles of nitrogen and hydrogen have also become constant, but we can't see that from the graph. For B, use the Chatelier's principle to identify which one of the curves, B, C, or D, represents an experiment carried out at the same temperature as experiment A, but at a higher pressure. Explain why this curve is different from curve A. So looking at the equation, we have 4 moles of gas on the left and 2 moles on the right. So that means that when we increase the pressure, the equilibrium shifts to decrease the pressure. So it favours the side with the least moles. And this is actually the right-hand side. And so when we raise the pressure, that means our yield of ammonia will increase. And so if we use the high pressure, that means that we have more moles of ammonia at the end. And so the curve we're looking for must be B, because that's the only curve which has more moles of ammonia at the end compared to A. For C, identify which one of the curves B, C, or D represents an experiment in which the conditions are the same as in experiment A, except that a catalyst is added to the reaction mixture. Explain your choice of curve. So the thing to remember about catalysts is that it doesn't affect the equilibrium. It only speeds up the rate of reaction by providing an alternative route with a lower activation energy. And so that means that the curve we're looking for must be C, because that is the only curve where the moles of ammonia at the end is the same as A, but the rate of reaction at the start has sped up significantly, so that actually our yield of product is a lot more than A. So feel free to pause the video again before we start on question 2. So give one reason why most collisions between gas phase reactants do not lead to a reaction. State and explain 2 ways of speeding up a gas phase reaction other than by changing the temperature. So one reason why most collisions between gas phase reactants don't lead to a reaction is that the reactants need to possess the right amount of energy, which we call the activation energy. So they either have to have the activation energy or more than the activation energy in order for a successful collision to happen. So need the activation energy required for a successful collision. And then state and explain 2 ways of speeding up a gas phase reaction. So it says in the question that you can change the temperature, or we can change the pressure if the moles of gas on each side of the equation are different. So we can alter the pressure, but that's only if different moles of gas on each side of equation or we can increase the concentration of something. So if we had A plus B goes to form C plus D, and that's a reversible reaction, if we increase the concentration of A, so we add more particles of A in, then the equilibrium will move to decrease the amount of A, so it'll produce more products by using up the A. And so that's something else that we could do to speed it up. Or the third option is to use a catalyst. So what a catalyst does is it provides an alternative route with a lower activation energy required for successful collision. So most of the particles, so a bigger proportion of the particles will have this energy required to react. So lower activation energy required for a reaction.